In this part, we will see how the interplay between surface tension and the inertia of fluids dictates the dynamic behavior of soap films, liquid sheets, the fate of drops impacting solid or liquid surfaces, and the characteristics of surface wave. Soap films are the elementary brick of foams that we find in many applications, from shaving cream to food industry. In this first experiment, we follow at 2000 frames per second the bursting of a soap film held on a circular ring. A hole created in the center of the film expands radially with a speed measured at 7 meters per second. The radius of the ring is 9 centimeters and the whole phenomenon lasts only 13 milliseconds. Quantitative studies show that the thicker the soap film, the slower the opening velocity. They also show that this velocity does not depend on the liquid viscosity, provided the viscosity does not exceed 10 times the viscosity of water. So the question I would like to address with you is the bursting velocity of a soap film. So the experiment that you have shown consists of a soap film which is bursting. We call the size of the hole R, and the velocity of bursting is this velocity that opens the hole. If we look at what the experiment tells us, we first observe that this bursting velocity is of the order of few meters per second and depends on the thickness of the soap film, which is in micrometers. And the experiment tells us that the thicker the film, so for example on the experiment you have just shown, the thickness was 1 micron and the velocity was 7 meters per second. And if you increase the thickness, the velocity decreases. The slope here on a log-log plot is -1/2, which tells you that the velocity goes like 1 over the square root of h, which means that to decrease the velocity by a factor of 2, you need to increase the thickness by a factor of 4. So this is an experimental input, right, in your understanding. The other input is that the velocity does not depend on the viscosity of the liquid. So these are the information that the experiment tells us. So the velocity goes like 1 over the square root of h and does not depend on the viscosity. And these two elements are the one we have to recover with the model that we are going to develop. So if we start the analysis of our problem with the usual ingredient that we manage with, so the energy balance will tell us that the surface that has been consumed, so the surface is P r square when the size of the hole is r. We have two interfaces, and so the energy that has been consumed, so this is the capillary energy, or the surface energy, should go in kinetic energy, so 1/2 of the mass, so pi r squared times the thickness of the film times the density times the velocity of opening v squared. And so this balance, so this is the kinetic energy, gives you very quickly an expression for the velocity of opening. And so this velocity goes like the square root of 4 times surface tension divided by density and the thickness of the film. So this is our first evaluation of the bursting velocity. And now we have to discuss if it satisfies what has been observed experimentally. So what this formula tells us is that indeed the velocity is expected to go like 1 over the square root of h. So this is compatible. It also tells us that the velocity does not depend on the viscosity of the liquid. It only depends on surface tension, density, and thickness. And so for now we have the feeling that we are on the good road, right? But something special happens when you put the order of magnitude. So if you look at the value of the velocity of bursting, so you get that the velocity goes like square root of 4 times the surface tension of a soap film is of the order of 25 10 to the minus 3, divided by density of the liquid, 10 to the 3, and the thickness is 1 micron, so 10 to the minus 6, then this gives you 10 meters per second, which is a little bit larger than the 7 meters per second that has been observed experimentally. And so even if this model contains good ingredient, we overestimate a little bit the velocity, and we have to develop a more precise model in order to get closer to the experimental result. So in order to correct the problem that we have just underlined, which is a numerical factor in front of the expression of the velocity, we are going to use another way to evaluate the velocity of opening of the hole. And so this other way is based on momentum. And to understand what I mean by momentum, what we are going to do is to make a cut is this soap film, and to look from the side. So if we look from the side, what we see is that we have a soap film of thickness h with a rim here. So the liquid is there. So there we have the thickness of the film h. The same thing on the other side. And the collected liquid here has a mass m and moves, so the rim moves at the velocity that we are trying to find. So in this system, if we write the momentum evolution, what we get is that d over dt of the mass of the rim times the velocity of the rim should be equal to the forces that apply on the rim. And the forces are surface tension forces. And so we know exactly the expression, so it's 2 pi r times gamma times the two sides of the soap films. And so what we are missing now, since we are looking for a constant velocity, we can move this one out of the derivative. And so we have v dm dt that should go like 4 pi times the radius times gamma. And we know also that dm dt, so the mass collected in the rim per unit of time, will go like 2 pi r times the thickness times the velocity. And so when we put these two expressions together, then this allows us to find that the velocity should go like square root of twice gamma divided by the density times the film thickness. And this is the new expression of the bursting velocity. So now we have almost the same expression as before. So we have the dependency of the velocity like 1 over the square root of h. We have a velocity that does not depend on the viscosity, but the velocity is a little bit lower by a factor of square root of 2. And so when you calculate this order, you find that the velocity should be of the order of 7 meters per second. And this is closer to what we have observed experimentally. So the last question we have to deal with together is, why do we have a difference between the momentum approach and the energy approach? So the last question we want to answer is, why is the energetical approach wrong? And so in the general case, so we are going to show that there is a problem with what we did. So we start from our momentum equation that tells us that the evolution of momentum is a function of the forces applied to the systems. And so if we imagine conservative forces, so coming from a potential energy that I call EP, then we have this general relationship. We can remove the dt using that the velocity v goes like dx dt, and we end up with the following thing. We end up with d over dx of 1/2 of mv squared plus the potential energy, which should be equal to minus v squared over 2 times m dx. And this expression tells us that the total energy, so 1/2 of mv squared plus the potential energy, is only conserved in the system when there is no variation of mass. And in our system, when the rim is moving, then the mass of the rim increases. And so this means that the right-hand side here is not 0, and so we will have an evolution of this quantity. And what we can tell is that if m increase, that this quantity is going to decrease. Right? And so this is the origin of the difference between the momentum argument that gives us the good velocity and the energetical argument, which is wrong because we have forgotten this input. So if the energetical argument is wrong, what we conclude is that the good expression for the bursting velocity, and this will be our conclusion for this section, is that the velocity of bursting, v, is equal to square root of twice surface tension divided by the density and the thickness of the film. And this is a very useful result, which is going to be important to analyze the other experiment we have in this section. In many applications, like combustion engines, treatments of crops, or in spray painting, the liquid is stored in a tank and used as droplets. To transform the large volume of the tank into droplets, we first force the liquid from the tank to spread into a liquid sheet which breaks into droplets. This is an experiment that we can do in the kitchen, making an impact of the flow from the faucet onto a spoon. We look here at a more controlled version of the experiment, with the laminar jet impacting a flat metal disc. Water expands radially in a thin sheet up to a radius where it disintegrates into drops. Quantitatively, the radius of the liquid sheet increases as the jet velocity is squared. So each time we want to transform the liquid contained in a tank into droplets, there is an intermediate stage which is the liquid sheet. And so the question we are going to discuss now is what fixes the size of those liquid sheets. The way we produce the liquid sheet, the one that we are going to discuss, is the following. So we impact a jet on a disk, it spreads outwards and reaches a maximum size. The jet is cylindrical, and so we have the same thing on the other side, and produces an axisymmetric liquid sheet. The question is, what fixes the size that we call R, knowing that the initial diameter of the jet is d naught and the initial velocity u naught. When we do the experiment, these are the following observations that we can make. First, so we are going to put the size of the liquid sheet scaled by the initial diameter as a function of the velocity. So this one does not have any dimension, it's the ratio of two length scale, and the velocity will be here u naught in meters per second. When we do the experiment, we have several regimes, mainly two. So the first one, where the size increases with the velocity. On a log-log plot, it goes like the square of the velocity, and then at one point it changes its behavior and starts to decrease in size. And so then we wonder, why do we have this different behavior? And what we see on the movie is that in the first regime, so when the size increases with the velocity, we have a smooth liquid sheet up to the edges, so similar to the one that I have just drawn. Whereas on the other side, we have a flag behavior, so the liquid sheets start to oscillate due to his interaction with the air on both sides, so like flapping like a flag. And in this flapping regime, then the size decreases as we increase the velocity. So we have mainly two behaviors, one where air matters and the other one where air can be forgotten. So a final comment on this curve is that the typical value for the transition are for the velocity 8 meters per second, so the liquid sheets are observed between 1 and 8 meters per second, and the spreading of the liquid sheet can go up to 70 diameters. So these are typical values that characterize the phenomenon and the transition from no air to air sensitivity. So to understand this behavior, we need several inputs. So in fact, we need three inputs. The first one is that the velocity in the liquid sheet, so here, u is the initial velocity because there is very low friction. So u does not depend on r, is constant and equal to u naught. The second input is that the thickness of the liquid sheet, h, does depend on the radius. Because if you apply conservation of flux between the input and the output, then what you get is that 2 pi r h of r times the local velocity u naught should be equal to the mass flux that you have initially, which is pi d naught square over 4 times u naught. And this information tells you that h is such that you have this relationship, so it goes like d naught square divided by hr. And so you have an hyperbolic behavior, so the larger the distance from the impact, the smaller the thickness of the liquid sheets. The last input is that the velocity of the rim, so this one, is sensitive to the thickness. So we have shown with the bursting of a soap film that the velocity of the rim, so this one, velocity of the rim, goes like square root of 2 times gamma divided by rho h. And so if h decrease, the velocity of the rim increase. And so these two information allow us to look at how the velocity evolve in the liquid sheet. So we have first the velocity of the liquid that we have called u. So the velocity of the liquid is here. So it's constant and equal to u naught. And we then put the velocity of the rim. And the velocity of the rim goes like this square root of r. So this is the velocity of the rim. And what we observe on these two curves is that there is one special location which is going to fix the size of the liquid sheet, for which the two velocities are equal, which means that the rim is able to sustain the velocity imposed by the liquid sheet. And the expression of r is that it goes like rho u naught square times d naught divided by 16 gamma times d naught. And so this expression allows us to understand what we have obtained experimentally, which is that the radius of the liquid sheet evolves like the velocity square and does not depend on the viscosity. So the only ingredient that impose the radius of the liquid sheet, or the density of the liquid, the diameter of the initial jet, the velocity square that we have imposed, and the surface tension. It turns out that this number which appear here and that does not have any dimension, non-dimensional number that compare inertial effects to surface tension effect, is called the Weber number. So our conclusion as far as the size of the liquid sheet is concerned is that R over d naught will go like the Weber number divided by 16, where the Weber number is the non-dimensional number that compares inertial effect to surface tension effect and writes rho u naught square times d naught divided by gamma. So this is our final answer to the question. If the impactor is not well prepared to produce an horizontal liquid sheet, the impact of a cylindrical jet onto a disk of similar diameter produces a water bell, that is, a closed liquid sheet. Perhaps the most striking feature of these bells is that gravity is not responsible for their closing. An horizontal impact of the same jet onto the same disk produces exactly the same shape. Liquid sheets are not always flat, and so the question I would like to discuss is the shape of water bells. So water bells are obtained almost with the same experimental setup as the one for liquid sheets. So we have a cylindrical jet that impinges a disk, and if we do not manage to have an horizontal ejection, so we are going to observe a closed shape, symmetrical, and this is what we call water bell. So the difference with the liquid sheet is that now the ejection angle is smaller than pi over 2. So pi over 2 is for the liquid sheet. If we have an ejection with a smaller angle, then the liquid sheet closes and we call it a water bell. The information that we have about this water bell is that this shape does not depend on gravity, which means that if I make the impact horizontally, then I'm going to find exactly the same closed shape, provided I use diameter which are not too large compared to the capillary length. And so the question we would like to answer is, what is the origin of this closed shape, or what is the size of those water bell? So if I plot here the maximum extension of the water bell, I would like to know what fixes R, knowing that the initial jet diameter is d naught and the initial velocity u naught. The experimental result tells us that the size of the water bell is going to be a function of the Weber number, so rho u naught square d naught divided by gamma, time a function of the ejection angle. And this function is an increasing function, so the larger psi naught, the larger the extension of the water bell. And there is one value that we know is for psi naught equal pi over 2, we know that f is equal to 1 over 16. And the idea is to try to understand the origin of this dependency. So if we want to understand the size of water bells, we need to move into the liquid sheet. So what do I mean? So we have the jet coming out, expanding with an initial angle psi naught. This in a symmetrical way. And we now move into the liquid sheet and define several parameters which are going to be useful to understand this shape. So the first one is one of the radius of curvature, the azimuthal one that I call R1. And the second one is the radius of curvature in the plane of the blackboard that I call R2. These two radii of curvature are going to play a role in the shape together with the film thickness h. So to understand the shape, we are going to balance two types of pressure. The first one is the centrifugal pressure, so based on R2, so the liquid feels a centrifugal acceleration on the yellow radius of curvature, and the pressure variation associated to this centrifugal effect scale like rho u naught squared divided by R2 times h, and this is going to be balanced by the capillary pressure, so which is gamma times twice, because there are two sides for the interface, times the two radius of curvature, so 1 over R1 plus 1 over R2. So these two terms balance the centrifugal pressure, which tends to open the bell. So this one is responsible for the opening of the liquid sheet, and is balanced by the capillary pressure, which is responsible to the closing. So capillarity wants to minimize the surface, whereas inertia wants to open and go straight. So this is in fact the basic idea that describes the shape of the bell. We have to add the conservation of mass, which is going to tell us that the thickness is not uniform along the bell, but depends on the distance from the axis. And so for this, we just write the conservation of flux between the input. So we have a diameter d naught feed by a velocity u naught. And so what we get is that 2 pi times R1 times h times u naught should be equal to pi d naught square over 4 times u naught. And so this relationship closes the problem. So it gives us the expression for the thickness that appear here, like d naught square divided by 8 times R1. And so using this expression for the film thickness into the balance of pressure, this gives us the scaling for the size of the water bell. So we get the R1 over d naught is going to be function of the Weber number, so rho u naught square time d naught divided by gamma time a function of the ejection angle. And so this is one way to, let's say, discuss the shape of water belts and connect them to liquid sheets. So liquid sheets will be obtained when psi naught equal pi over 2, and then we will have a factor 1 over 16. And if it's different from pi over 2, then the liquid sheet will close and will follow some kind of the same kind of evolution.